Hello and welcome to this video tutorial. Today we're going to be looking at an application of the conservation of energy, specifically called the first law of thermodynamics. First, let's review what it is. Now, the conservation of energy law tells you the total amount of energy remains constant. Okay, well, if you add heat to a gas and you do work on a gas, both of those together are going to increase the kinetic and overall internal energy of the gas molecules, meaning the sum total of the heat added and the work done to compress a gas. This is the work done to compress a gas is equal to the change in internal energy, specifically in that case, an increase in internal energy. Okay. The flip side, the opposite perspective, of course, would be if you have heat that is added, we have to subtract any work done by an expanding gas. Okay, think about that. The work done on a gas and the work done by a gas are just opposite in sign. So for instance, if 100 joules of work is done on a gas to compress it, then a negative 100 joules is done by that gas as it is compressed. Okay, so keep in mind of how we can view different forms of first law. So we have the heat added minus any work done by the gas is also equal to the change in the gas's internal energy. So just remind yourself about the variables, and then we'll go ahead and begin. Okay, delta U is the change in internal energy in joules. And keep in mind, delta U is going to be equal to U final minus U initial. So U is the internal energy. So the final internal energy minus the initial internal energy is the change in internal energy. Q is the heat transferred to the gas. Okay, now something to consider, it's also in joules. Positive Q means heat was added. Negative Q means heat was removed. Okay, and then finally, W, right, represents the work done. Again, also in joules. All right, let's go ahead and begin a look at these practice questions. Question number 1, read along with me. Remember, as you begin, ladies and gentlemen, you should have your calculator out and ready. Please pause or rewind the video as you need to. When it comes time to do a calculation, pause the video, try the calculation yourself, and then resume the video to see whether or not you're doing it correctly. Read along with me, please. A system's internal energy is 39 joules, the initial internal energy. If then 114 joules of energy is transferred to the system as heat, the final internal energy is 163 joules. How much work is done? Okay, so we're looking for the work done. Okay, now it says on or by the system. So what we're going to do is we're going to essentially answer it one way. And then, of course, like we're going to answer for the work done on the system, on the gas. And by system is referred to as gas. If we find the work done on a gas, then the work done by that gas would just be the negative of that previous calculation. So let's go ahead and try. So we're looking for the work done. The heat that is transferred and added, so it's transferred to the system. So it's positive Q, positive 114 joules. And then the internal energy change is going to be U final minus U initial, which would be the final of 163 joules minus the initial internal energy of 39 joules. Go ahead and subtract that, and we get 124 joules. Okay, so we have everything set up, ready to calculate. Okay, I'm going to split the rest of this page in half. So what we're going to do is we're going to look at it from two different perspectives. Like I said, I'm going to show it to you once, and then for the next few problems, you'll see kind of the shortcut that can be assumed as we go. So we're going to go change in internal energy is equal to the amount of heat added plus the work done on the gas. We don't really know if the gas was compressed or if it was expanded. We don't know. So that's why essentially we're answering two different possibilities. If it was compressed, here's how much work was done. If it was expanded, here's how much work was done. So we're solving for work, and to do that, you need to subtract Q, right, from both sides. So the work done on the gas to compress it would be the change in internal energy minus the heat, which would be 124 joules of an increase in internal energy minus the 114 joules of heat that was added, right? And the work done would be 10 joules of work done on the gas. Okay, now if I took a look at it from the opposite point of view, Q minus the work done by the gas, okay, let's say the gas was being compressed, okay, that means that means 10 joules of gas, 10 joules of work done on the gas is negative 10 joules of work done by the gas, okay? So let's just see it play out. Well, what I'm going to do is I'm going to solve for work. I can do that by adding the work over to the left and subtracting the change in internal energy over to the right, and they swap places. So the work done by the gas is equal to the Q minus the change in internal energy, okay, which would be 114 joules minus 124 joules to give you, guess what, negative 10 joules, just like we said. Okay, and then just as a matter of perspective, done by the gas. Okay, number 2, a system's initial internal energy is 8,093 joules. Then 6,932 joules of energy is transferred to the system as heat. There's our positive Q. If the final internal energy is 2.092 times 10 to the 4 joules, how much work is done? Okay, number 2 is very much the same problem as number 1. At this point, go ahead and pause the video, try to complete number 2 on your own, and then resume to see if you did it right. Go ahead and pause right now. All right, let's see how you did. Okay, so the unknown is the work. We added 6,932 joules of heat, right, positive. And the internal energy change would be 2.092 times 10 to the 4 joules minus the 8,093 joules. Okay, so subtracting those, we get about 12,827 joules. Now, for the moment, I'm going to keep all 5 digits of significance here. I'm only going to round the answer at the very end. We never do any rounding partway through a problem, so I'm going to keep all 5 digits of significance there. So we've got change in internal energy, and I've got Q. Okay, so if delta U equals the heat added plus the work done on the gas, again, solving for work, I'm going to subtract Q from both sides, and the work done on the gas is equal to the change in internal energy minus the heat added. Plugging in, we have 12,827 joules minus 6,932 joules, which gives you about 5,895-ish joules. And we'll just go ahead and round that up. We'll round that up to 5,900 joules. Okay, so you have 5,900 joules of work done on the gas. Okay, well, what's the flip side? Or negative 5,900 joules of work done by the gas. Question number 3. When 867 joules of heat energy is added, so there's our positive Q, the expanding gas, this time we are told that expansion happens. So the expanding gas does 623 joules of work. What is the overall change in internal energy? We're looking for delta U. So delta U is the unknown. Q is 867 joules of heat added. The work done by the gas to expand against its surroundings is 623 joules of work. Okay, the equation we use for an expanding gas situation is the change in internal energy is equal to the heat added minus the work done by the gas. Since the change in internal energy delta U is already isolated for, just go ahead and plug in. We have 867 joules minus 623 joules. Subtracting those, get about 244 joules. Okay, so again, if there's any part of this video you needed to see again, please remember to pause, rewind, and reset that video to help make it a little clearer. I do hope you found this tutorial to be helpful. See you next time.